is located. So we have our natural gas that will go to the acid gas removal unit. Okay, this is the main step that we will remove H2S from and CO2 from natural gas. This is the main unit that we will remove H2S and CO2, that we will produce acid gas. This combination is called acid gas. But now CO2 doesn't have a lot of value while H2S has a good value. We can convert it to sulfur, elemental sulfur. We can extract elemental sulfur from in H2S, and we can convert it. Then sulfur, elemental sulfur has a lot of application, can be sold, with higher price. And then, so it's better to take advantage of this H2S that is available widely in natural gas and convert it to elemental sulfur S and sell it. So for this, what we will do, we will send this acid gas to the sulfur recovery that we already talked about that in more in detail. It was kind of long unit that you also saw the videos. And after sulfur recovery, you have your elemental sulfur plus some other product that is produced in this process that you will send it to storage. But sulfur recovery unit, if you remember, the closed process is the main process in this unit that has two reactors. One furnace reactor and then a catalytic reactor. And in closed process, we need to have our acid gas to be pure in H2S. Okay, we need to have an acid gas that is pure in H2S, then we will send it to sulfur recovery unit or closed process. All right. So to the process, the acid gas after acid gas removal unit has, I think, about 20%, 23% of H2S, some water, some hydrocarbon, and CO2. Okay, we will see the exact number later in this unit, in this video. So it doesn't have that much H2S. What we will do, we have to first sending it to a unit to separate CO2 from H2S, and then send a stream that is pure in H2S to sulfur recovery. So acid gas enrichment is exactly for this purpose. It's a process that you send acid gas, you try to separate as much as CO2 from the process, and you will send the remaining stream, which is pure in H2S, to sulfur recovery unit. This is the whole purpose of this acid enrichment process. So CO2, okay. CO2 removed from natural gas in the acid gas. Let me go through this slide. I can use this to presentation. So the acid gas that is removed from natural gas in the acid gas removal, okay, this stream here, it contains H2S and CO2. It has a large amount of CO2. This CO2, if it goes to the sulfur recovery unit or closed unit, okay, closed process, it acts as an inert gas. CO2 is an inert, it's a very stable molecule. It doesn't react easily with any component. So if CO2 goes through this sulfur recovery or closed unit, it will act as an inert gas. So you are sending an inert gas that cannot be processed. So like this inert gas led to increasing the size of your unit, and also for sure it will reduce the sulfur recovery efficiency. So in order for closed process, to work efficiently, and in order to minimize the size of equipment, the size of the process, so we have to try to separate CO2 from H2S. The H2S that is entering to the CO2 to sulfur recovery unit, it has to be high in H2S. The amount of H2S has to be high, and the amount of SO2 need to be low, because SO2 is an inert gas in this process. And also any other hydrocarbon that is available in, because in acid gas removal, we don't only remove CO2 and H2S. We also remove some hydrocarbons here. Some hydrocarbons will be also removed here, hydrocarbons, right? So we need to also try to minimize the amount of hydrocarbon going to sulfur recovery process. So based on the information available, if the feed to the closed unit contain less than 40 mole% of H2S, okay, so the efficiency of the closed units to recover sulfur will be very low. So if the feed here, I'm talking, okay, let me just clean this slide a bit. So the unit, I mean the stream that is going to sulfur recovery unit, to closed unit, it has less than 40 mole% H2S. So we say that there are too many inert gas present in this stream, that it will be very hard for closed unit to maintain a stable flame in the main burner. Okay, so you know that in closed unit, let me go back to some slide that I have here. So this is the closed unit in the sulfur recovery, that you will send your gas to a furnace. Okay, this furnace has a flame, as you can see, and then it goes through a catalytic reaction, catalytic reactor. So we have two steps: furnace, burner, and catalytic reactor. So if the amount of CO2 in this unit is lower than 40 mole%, in this case, we say that there are a lot of inert present, that we cannot have such a stable flame in this burner. Then, to minimize the size of the closed unit and maximize the efficiency, the feed gas has to be enriched by selectively removing the H2S from the regenerator of gas in a second amine absorption. So, like, the acid gas is coming from where? This is a typical absorption stripping unit. We already talked in acid gas removal unit 2 of this course, the video number 2. We already explained this unit. So you will send your sour gas, okay, to the absorber. At the top, you will receive your sweet gas. Then you have at the top here, you have a counter current flow. At the top, you have lean amine. At the bottom, you have a rich amine. It's rich in H2S and CO2. Then your amine goes to the regenerator. Now you have an amine which is rich in H2S and CO2. So it goes to the regenerator, which is a distillation column. At the end, you will remove your acid gas, which is H2S and CO2. Okay, H2S, CO2, that we call it also off gas. Okay, this also called off gas. And then you have also a lean amine that goes back to the absorber. Okay, goes back to the absorber. So this off gas, now it has H2S and CO2. It will be sent to a acid enrichment unit, which is exactly the same process. But in that process, we will use another type of amine, another type of solvent, that now the solvent separate H2S from CO2. This solvent that we have here, it separates both H2S, CO2 from natural gas, and it gives us a sweet natural gas. But in acid gas enrichment, we use exactly the same process, but with another type of solvent that will separate CO2 from H2S. So this is this process here, okay, that now we will send a gas, H2S, acid gas, H2S and CO2. It goes through the different steps, and at the end I have my Now I have my off gas here, which will be mainly CO2 in the acid gas enrichment, okay, which is CO2, and I have another stream which is pure in H2S. So this is called the second, second amine absorption step or acid gas enrichment. The off gas from the second amine regenerator will contain more than 40 mole% of H2S, which is suitable for Claus process. So like now we have kind of two off gas or two gas stream. Okay, this is your first off gas that has majority CO2. You have another off gas or another stream that has majority H2S. So now this stream that is pure in H2S is a good feed for Claus process or for sulfur recovery unit. Then, okay. The feed gas from the acid gas removal unit it means this stream. The feed gas from acid gas removal unit, okay, this unit has approximately the following properties. Here you have many components, okay, you have many components like H2S, CO2, some hydrocarbons, and water vapor, okay, H2S. So this H2S now, this H2S has, here you have almost 22.5%. Then you will send it to this acid gas removal unit. At the end, you will get a stream that has about 40% of H2S, more than 40%, which is suitable for sulfur recovery unit. So this mixture here, the feed here, it has all these parameters, okay? It, like in the condition that we have in the Claus process, okay, we have which is high temperature, condition, we have a furnace. So these components, these molecules that we have, they cannot only form COS or CS2, okay, which is, like some contaminants, some undesired products. They can also produce soot. Soot, is also kind of coke, like they call it also coke. Like if you see, like your car exhaust, if the engine, is not working properly, so you might see, like if you touch the exhaust pipe, the tubes, you can see that there are some kind of black, black solid particle attached to it. That is soot. That is the kind of, like burned carbon, okay, that if this soot, which is, that is available in this stream here, both here and here, okay, it goes to the reactor, to the Claus reactor, that as I showed to you, in the Claus process, we have both reactor and furnace. So the soot is kind of, it can poison the catalyst. It can deactivate the catalyst, and it can also, reduce the life of catalyst, so it decrease the efficiency of process. So like these components, when they go to the furnace all together, when they go to the furnace, they can produce soot. Then soot can go to the catalytic reactors, and it can deactivate the catalyst and reduce the efficiency of the process. Now, okay. So what will happen? We have our acid gas, which is mainly H2S and CO2. Okay, we call it here feed gas. It enters the enrichment section. So this process, which is exactly similar to acid gas removal. So first it goes to the knockout drum, because like this feed gas might have some water, some liquid content. So it goes first to a knockout drum. Okay. So here, like, you will remove any kind of contaminants liquid from the gas. Okay. Now this is like mainly this stream is mainly CO2 and H2S, although it has some kind of some other hydrocarbons. Okay. And water. So you remove any kind of liquid, any water liquid from the bottom, and you will send the other gas to the absorption column. So in the absorber, it will be fed to the absorber from the bottom, and at the top of the absorber you have a amine solvent, which is MDEA. MDEA I have shown here, like this is the molecular structure of MDEA, and it's called also metal. Just let me adjust this. Yeah, it's also called it is called methyl diethanolamine. Okay, MDEA, methyl diethanolamine. So this solvent, okay, it goes from top to the bottom. They will be in contact in the absorber, and this solvent selectively absorb H2S, and it doesn't care about CO2. So at the top you have a stream that is majority CO2. At the bottom you have an amine solvent that is rich in H2S. And this is the chemical reaction that happens in this reactor. Okay, H2S and CO2, how they are absorbed in this absorber. Then what will happen? You have this rich amine, okay, that absorb H2S and also some hydrocarbons. It is pumped from the base of the absorber by the rich MDEA pump. So here you have a pump that you will send it to a heat exchanger. So it's like absorber. You know that absorber works at low temperature and high pressure. Generator works at high pressure, high temperature, low pressure, right? So here you have temperature high. Temperature here is high. Temperature here in this absorber. Okay, let me just clean it a bit. So now I'm here. I'm up to here. Temperature in absorber is low. In generator is high. So what you can do, even the stream that is coming this way, since it's coming from generator, the temperature is high. So I have a low temperature stream that is coming from absorber and high pressure stream that is going to absorber. So I can contact them in the heat exchanger, and then this stream can transfer some of the heat to this stream, because this stream that is going to absorb it, I want it to be at lower temperature, and this stream that is going to the generator here, I need it to be at higher temperature. So I contact them in the heat exchanger. This is what I'm explaining here. So they can transfer the heat, and I can reach to the temperature that I want in each of these streams. Okay, so after that, the stream that is rich in amine, okay, the stream that is rich in amine here, okay, it goes to the regenerator. Okay, it will be moving downward. Like both of them are kind of like, this absorber is a tray absorber, and this is kind of tray distillation column. So it goes down, and you have also, okay, in the regenerator, at the bottom of regenerator, you have reboiler. At the top, you have condenser. So, like once the amine, which is rich in CO2, goes through this distillation column, at the bottom, you have a lean amine, which has a low amount of hydrocarbons, H2S, CO2, that will be pumped to the absorber. And at the top, you have a stream that is majority that has a high amount of H2S, more than 40%. Okay, so the heat, I mean, how the heat are provided here to this regenerator, since as I said, it works at high temperature. So this heat, it is provided by the reboiler that we have here. Okay, so this is the reboiler that you have that produce this heat or high temperature for us. The overhead vapor, okay, I'm talking about this part. The overhead vapor from the top of the regenerator is cooled and condensed by using a condenser. And then now after the condenser, it has both vapor and liquid. The liquid will be collected at the bottom and it will be sent back as a reflux to this distillation column. And the gas phase, which is majority H2S, it will be collected at the top and it will be sent to the class unit or to the sulfur recovery unit. Okay, so this is what I explained in this part. Okay, now some additional information here is that, okay, strip lean MDA from the base of the regenerator, okay, it means here, this is the stripped lean amine, okay, from the base of regenerator, is pumped by the lean MDEA pumps. So this is the pumps or boosters, MDEA pumps. And it will be first, it will go to the heat exchanger. I explained this already because here, since it's coming from bottom of generator that you have reboiler, it has high temperature, while in the absorber, I want low temperature. Here I have a rich amine that is in low temperature because coming from absorber, so I can contact them in this heat exchanger. They exchange some heat. What I get here is low temperature. What I get here is higher temperature. This is what I really want. Okay, so they are contacted in this heat exchanger, and this lean amine will be gone to the absorber. A side stream from this return flow is diverted and through a series of filters to prevent the buildup of impurities that reduce the efficiency of solvent and permanent foaming. So it's saying that here you have lean amine, you take a side stream, okay, not all of them, just because that filter create a huge pressure drop, so we cannot send all the streams to filters and filter them. So we will use a filtering system as side stream here. We send some of this lean amine to the filter to remove any buildup of impurities. It can be any kind of impurities, some solid particles, some solid impurities. We remove them to make sure that we have low amount of impurities in the lean amine that is going to absorb it. If we have high amount of impurities like solid particulates, so it can significantly decrease the absorption process here, the absorption, and also it can create foaming. Okay, that foaming, promote foaming, that will be a big issue for us. The acid gas from the enriched section has the following approximate analysis. So as I said, here it has about 23%, and at the end here it has about 60% H2S. Okay, H2S. So it comes with 23, it leaves at about 60. So this is the specification of the stream that we have at the end. And you see that still it has a high amount of CO2, but it doesn't have that much hydrocarbon. And water content is almost the same, doesn't change a lot, which is not also very problematic. But, sorry. But the most important thing is that we reach to a specification for H2S that we need for sulfur recovery unit or class process. And okay, so in this slide we just kind of compare, what will happen before acid enrichment unit and after acid enrichment unit. Okay, I'm talking about this part. Before acid gas enrichment is here, after is here. So before and after. So before, this is your specification, and after, this is your specification. The most important thing that I said, we need to higher concentration, more than 40% of H2S at the end to make sure that class process will work efficiently. So that was almost all about this this process. Okay, as I saw, it was very short unit. So as a summary, acid gas enrichment is used as a second amine absorption. It uses MDEA as a solvent to remove CO2 from H2S. So it will increase the concentration of H2S in the acid gas stream from 22.5 to more than 90%. In this case of this example, it was about 60%. And also, in the same time, it will remove hydrocarbons. 90%, the amount of hydrocarbon will also decrease. You see that at the beginning, before the hydrocarbon content is 9%, at the end is very low, it's trace. So it's a good process. So what will happen to this hydrocarbon? The hydrocarbon will be removed here. You can see the fuel. So the rich amine that has H2S and hydrocarbon, it will be first sent to a flash tank. Then in the flash tank, the hydrocarbons will be removed, that we call it also fuel. So that was all about this unit. I hope you enjoy it. And please let me know if you have any question. If you need any more explanation, I will be happy to help you. And thank you, and see you in the next video.